Number 27. In the text, it was shown that N over V is equal to 2.68 times 10 to the 25th meter to the minus 3 for a gas at STP. Show that this quantity is equivalent to N over V of 2.68 times 10 to the 19th centimeter to the minus 3. So first thing is, you don't need to know it, but for this problem, but you should know it. Standard temperature and pressure, STP. What is the standard temperature? I'll write that as T sub S. It's 273 Kelvin. Please memorize that. And what's the standard pressure? What's 1 atmosphere, or aka 1.013 times 10 to the 5th pascals? This you have to memorize. Anytime they talk about STP, those are the values for temperature and pressure. Now, getting back to the problem. We have to basically convert 2.68 times 10 to the 25th meter to the minus 3 into centimeter to the minus 3. So what I'm going to do is, I hope this is good at this point, mathematically speaking. Instead of writing meter to the minus 3, what I can do is I can inverse that and write 1 over meter to the positive 3. All right, that's the mathematical rule here. If you have something that looks like this, you have a, let's say, to the x, you can rewrite that as 1 over a to the minus x. Okay, another way to write that would be if you had a to the minus x, you would then rewrite that to 1 over a to the positive x. All right, so that's all I did here. Now what I simply have to do then is get rid of the meter. I put that on the top, centimeter on the bottom. I know there's 100 centimeters in a meter. And then I have to cube this result because I need the meters to cancel perfectly. And then I need cubic meters, cubic centimeters, right? So now all we have to do is plug this on in. So it's 2.68 times 10 to the 25th divided by then 100 cubed. And what do we get? We get 2.68 times 10 to the minus 19. Oh, that's exactly what they told us it should be. Very good. 2.68 times 10 to the minus 19. All right, and that's centimeter then cubed. Well, 1 over centimeter cubed, and then I can bring it back to centimeter to the minus 3. All right, good. Good enough, right? Moving on. Letter B. About how many atoms are there in one cubic micrometer? All right. So at STP, that is. Okay, so what we need to now do is we now need to use the ideal gas law. All right, I created a general video on this, so please check that out, what the variables represent here. All right, pressure in Pascal, volume in cubic meter. This is the number of moles. This is then the gas constant, and then our temperature. And actually, since they're asking us for atoms, a better formula to use would probably actually be this one. N, capital N R T. Or excuse me, N, they use the K for the Boltzmann constant, NKT. All right, so where N stands for the number of molecules or atoms. So now basically, we have the pressure they told us, and let me label this as part B. This was part A. So they told us now it's at STP, right? So I told you to memorize that here's the pressure at STP. So it's going to be 1.013 times 10 to the 5th Pascal multiplied by the volume. Now, what volume did they tell us? Well, it's talking about a cubic micrometer. But guess what? We need this in cubic meters. So we got to do a conversion. So we got 1 times, so we have 1 micrometer cubed. And now we have to convert that into meters cubed. So micrometer on the bottom, meter on the top. You have to know that there are 1 times, or basically just 10 to the 6 micrometers in a meter, and then you got to cube this result, all right, to get the appropriate units. So let's do this. So basically this will work out to be, this should then be 10 to the minus 18th, okay, cubic meters. All right, so that is now the cubic meter value. So that's what I'm going to plug in. So this is 10 to the minus 18. That will then equal the number of atoms, which is N, multiplied now by that Boltzmann constant, okay, which is 1.38 times 10 to the, what is it? I'm trying to remember, negative 23, right? All right. And then multiplied then by the Kelvin temperature, and again, it's at STP, so that's 273. 273. Now all you have to do is calculate this for N, so divide out these two terms, right, from both sides. So we'll get now N is equal to, and like I said, guys, take a look at the link below. I left it for that general video, all right? So this is 1.013 times 10 to the 5th times 10 raised to the negative 18th. And then we're going to divide that now by 1.38 times 10 to the negative 23 and multiply by 273. And here we go. So we have now about, what is this, 2.69 or so? 2.69 times 10 raised to the 3, 6, 7. So 7. 7. And this will be the number. This is basically the number, sorry, of atoms. All right. So in a little micrometer of space, there are about, what is that? 26 million, 27 million? Yeah, about 27 million atoms. Okay. So then let us see, what is your answer to part B imply about the separation of atoms and molecules? Well, you would have to then find, just because there's 27 million atoms in that amount of space, you'd have to really identify how big an atom is, right? You might say, well, that's a lot of atoms. There must not be a lot of space. Well, not if the atoms are super, 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 super tiny, right? So you would want to now consider the size of an atom. And then you can figure out, how much space there really is. It's going to be, there's a lot of separation. That's basically the answer, okay? All right, guys, so thanks for tuning in. Hope this helped. Please remember to subscribe. We'll see you next time.